Welcome everyone to my linear algebra recap. So this is for my lecture that I took in the first semester. So here it is. I took linear algebra 2020, so it's been a while. So that's why the purpose of this one is actually for me to remember everything that I did again. And hopefully if someone finds it useful, I would be happy as well. If you guys learn something from it, get an intuition from it, because I'll also be making some animations where hopefully you can get a better idea on the topics. So first and foremost, I'll go over linear systems. So the purpose of linear algebra, what it is, and then also look at some simple, or just, algebra of matrices and the properties. Next up, we'll look at how we can get to solutions. We'll go through the inverse, Cholesky, different decompositions. I also have animations of these, hopefully to better understand the topic. And then we'll look at vector spaces, different matrix properties, their norm, what a norm is, orthogonality, the determinants. Also, eigenvalues and eigenvectors is a pretty important part. And also, we'll look at special matrices, square matrices, symmetric, what each of these ones entail, or, what kind of simplifications we can do. What a normal, orthogonal, triangular, diagonal, nilpotent, skew-symmetric, positive, definite, one of the most important ones, and idempotent. And at last, covariance, correlation, stochastics, because I want to go to that field, quant finance. Hopefully I can get into it. So yeah, that's why I'm also looking at that. So yeah, and if anyone has something that I missed and think that it's important, please put it in the comments so I can also learn about it. Okay, so next up, we'll first look at what a linear systems is, the purpose of linear algebra. So I bet most of you have seen this. We have two equations, two unknowns, x plus y equals 3, 2x minus y equals 0. We can find a solution to unknowns to equations. So yeah, we can check if x is equal to 1, y is equal to 2. We have a solution. 2 minus 2 is 0, and 1 plus 2 equals 3. So this happens a lot, or I'll talk about the y later, but this one we can also use matrices to write it down like this. 1x, 1y equals 3, 2x minus y equals 0. So that ax equals b. So maybe I'll look at it later. But yeah, so there's like a matrix notations. So why do we do this? So of course, if we have a matrices, we can make it infinite or super large for the computer to compute it. Like this, we need to calculate by hand. It's impossible if we have large systems. And yeah, with the computer, we can automate it. So yeah, and one of the thing is linear systems are an approximation of reality, because we can do Taylor expansion, and the first degree is pretty much we can use this as a matrix notation. So yeah, linear systems are an approximation of reality. That's why we have that a lot. We see it in control systems, when we want to control system, I guess, a plant production. Then we see this equation. It's used a lot for signal processing, kernels, machine learning. We use it a lot. Backpropagation when we calculate things. Yeah, we have neural networks are pretty much, we use linear algebra. Of course, we have some linearity, but still linear algebra knowledge is welcomed. PCA, principal component analysis. It's pretty much singular value decomposition. So that's also linear algebra. For, yeah, we have like rotations, everything for transformations, which is in robotics, graphics, computer vision. We use linear algebra or matrices. And for optimizations or compression of data, we also use this. So yeah, let's actually look at what a matrix transformation is, or what happens. So here we see in this example, 1, 1, 2, minus 1, and B we have 3, 0. I'll use the same example. Yeah, I wrote some different scripts. Now let's look at the first one. So here we see we start, so this is where we end at 3, 0. Is this the right one? Yeah, 3, 0. And we see like this is our matrix. I inputted it here, but yeah, this is what the transformation does. And what here I already inputted like the starting value, but as we see, it was like x equals 1, y equals 2 was the solution. So when we start out here and we do our matrix, we'll get to our output B here at 3, 0. And we see here we have the eigenvalues of our matrices. So, and lambda 2, or the E2, V2, I mean, has an eigenvalue of minus 1.7. So it flips the sign. And this one just stretches by 1.7. So we see the grid here. So matrix transformation is basically just scaling along the axis, the eigenaxis. So yeah, here we scale, and here we just flip and scale as well. Let's go back. So yeah, we saw this. So yeah, some different properties of matrices. So we see we have different linear systems. So for this one, we saw we would have like one unique solution, which is x equals 1, y equals 2, that we have this. And here, the unknown variables are exactly the same as the independent equation. So we have 2 unknowns, 2 equations. So yeah, the rank of matrix A is n, and it's also equals n. So the amount of unknowns, equations, yeah. Yeah, so rank is the number of independent equations, which is also the dimension of the image. So our output space, basically. So yeah, which B's are reachable, so which outputs are reachable states in control systems. Our kern, or null space, I think it's called, is M minus the rank of A. So it's all the vectors that are mapped to 0, and in this case, it will be 0. So yeah, it's the eigenspace for eigenvalues that are equal to 0. This is what the matrix forgets. Or yeah, so if you change the input, the output stays the same. Or yeah, in control systems, it will be like the uncontrollable modes. Or yeah, in machine learning, the redundant features. So it's yeah, when AX equals 0. So when we change something, it stays 0. So yeah, let's look at a different linear system. So for example here, x plus y equals 3, 2x plus 2y equals 6. So we see these are linear independent. It's basically the same information. So we only have one equation that gives us information, but we have 2 variables, 2 unknowns. So yeah, in the end, we can get a solution which is like x equals 3 minus y, but that means we have infinitely many solutions. So yeah, this one, the unknown variables are more than the independent equations. So yeah, here we would see the kern or null space as equals to 1. And also we would have different cases. So if we have something that's inconsistent, so one time it's equals 1, x plus y equals 1, x plus y equals 2. So here we would have a problem, But this is actually, so this we would not be able to solve by hand here, but it actually can happen in real life. For example, if this is a measurement, sometimes the measurements are inaccurate. So one time you measure it, it's equals to 1. One time you measure it, it equals to 2. So what do you do with linear algebra? You can still solve this one, or to get like the least square solution, so the best solution with least error, I guess. So yeah, normally it's like no solution because it's inconsistent. Or I mean, yeah. I mean, this one is more for these. Oh yeah, and here it's, well, I'll take it back. So this is no solution. But here we see, so here, for example, we do something, we have 2 unknowns, but we have 3 equations, we're overdetermined. So yeah, this one maybe the error is a bit large, but here it's more similar. So yeah, we can see the rank is larger than A, so it's overdetermined, and this, maybe this also, I don't know. But both, we should be able to solve it with like least squares, QR, or SVD, singular value decomposition. So yeah, let's actually look at some of these. Let's go back to my laptop. So here I have a different script, just a free matrix transformation. Oops, I think something's running. Oh wait, why did I get an error? Whatever. But yeah, so let's, one of the infinitely many solutions was if we have 1, 1, 2, 2. This would be this case. 1, 1, 2, 2. And then for B, we had x equals to 3 and y equals to 6. So it would be this point. So here we can see, so this would be the end. But we can see how, if we look at the grid, everything, it gets like squished together, like one of the eigenvalue, oh, this one does not display, but yeah, 1 goes in this direction, it stretches, and 1 reduces to 0. So we lose information. So we can see all these points that were on this line will end up here. So all these starting points are possible solutions for x equals 3 and y is 6. So yeah, here we see like this will end up here. Yeah. So that was 1. I think it's okay. Let's go back to my iPad. So yeah, some operations and properties of matrices. So yeah, A plus B we can do if it's the same shape. It would be just 1 plus 1 equals 1 plus 1, you know, just each cell adding cell. We can like times a scalar, it just scales each of the entries. Yeah, can apply this law. And then for matrix multiplication, we can do this allowed of the same columns of the first one as rows of the second. So if this and this is the same, and in the end we would get a matrix of size mn. So usually how I remember is if we have 2 matrices, the front and the top is going to be these 2, and what is in the middle is the dimension that needs to be the same. And matrices are not necessarily, what is it, cumulative? I don't know the word, but yeah, AB is now equal to BA. But if it's the same order, ABC, we can like first multiply BC or AB, it would be the same. And this also applies. So yeah, the order C applies to X, B applies to this, and then A applies to everything in front. So yeah, it's right to left when we do matrix multiplication. We can have the transpose of AT, we would just flip the signs. So yeah, so it's like this one would end up here, this one end up here. So yeah, we can also use complex numbers, but most of the time I'll just skip them. But for complex numbers, we would like flip the signs as well. And another rule, if we have AB transpose, we would end up with B transpose H transposed. And the determinant, we already looked at it a bit. It's the eigenvalues multiplied together. It's how much the matrix scales the input, so how much the volume grows. Or for example, if we look at the example, let me get back to my laptop. So yeah, it's how much the volume will change. So if we have look at one cell, okay, this might be not the best. It will like it will be like a huge cell. So before it like was like 1 times 1, and now it would end up like it's not, but like 1.7 times 1.7 maybe, something like that. Here. So yeah, oh yeah, here the determinant of AB is multiplied with each other. The transpose has the same determinant. If the determinant is not equals to 0, it means all the eigenvalues are a number and A is invertible. Of course, if it's a square matrix. Yeah, and the determinant of the inverse of A would be 1 over the determinant of A. So yeah, it undoes. So if A scales it, the inverse would scale it back. You know, if it makes it bigger, it would like make it back to the original place. The trace is just addition of all the eigenvalues. Yeah, the trace can also be the addition of the diagonals added together. So this can be used as a check, like determinant is the multiplication and the trace is the addition, so we can see if we calculate it correctly. So then some special matrices. In the end, I'll go over it like in more details. Yeah, we have square matrices if it's n times n, so the input and output are in the same space. Symmetric, if we take the transpose, it's the same. So what would that mean? It's diagonizable. It has real eigenvalues. We can do eigendecomposition. And a matrix is normal if A transpose A is equal to A transpose, and yeah, that means we can have or like make an orthogonal eigenbasis of the matrix. Orthogonal means Q transpose times Q equals to the identity matrix. So yeah, Q transpose has to be equal to the inverse. So that means it's norm preserving, it does not scale it. The determinant is either 1 or minus 1. The eigenvalues are on the unit circle. It basically means it just like rotates it usually. It does not, yeah. So normal would preserve the angles of the matrix. We have triangular. That means if we only have values on the upper triangle, for example here, only on the upper side, and all zeros on the lower side, or on one side. So yeah, the eigenvalues would be on the diagonals. The determinant is just the multiplication of those lambdas, and it's super easy, or it's easier to calculate the power of it. And this is also trivial to solve for the solution because we can just substitute it, substitute the numbers. That's why we'll see some decompositions will make the matrix into two triangulars. We have diagonal matrices. That means it only has values on the diagonal. It's super easy powers. Inverse is super easy to calculate. Exponential is easy. So that's why we always love getting diagonal or to diagonalize our matrices. Nilpotent means if at a certain point, if we take the power of a, it will equal to 0. That means all the eigenvalues are 0. And there's a finite e to the power of at. And yeah, we will see some different operations. It's also easy to calculate. Scalar matrices, lambda I, well, so not much about that. Skew-symmetric is if the transposed is equal to the negative of a. Positive definite if all or this is larger than 0. So for all x not equal to 0. And we love this as well. Idempotent is if we take the power, we get the same thing back. And singular is if a matrix is not invertible, so one of our eigenvectors goes to 0, so we lose information. Stochastic, it's non-negative, and the rows and columns sum to 1. We have sparse matrices if there are many zeros. Yeah. So let's look at the inverse. So A times the A inverse would give us the identity matrix. Identity matrix would do nothing to our value. So if we have, I don't know, it's like this, 1, 1, 0, 0. And if we have x, y, we would just get back x, y. Yeah, because it's just x, y, whatever. So yeah. So here's if we take the inverse of AB, get BA inverse, the transpose, we can take it in. And if we have a scalar, we have to 1 divided by alpha. So yeah, let's look at this, how we would solve this problem. So here we see we have a square matrix and we have one unique solution. That means we can have an inverse. So if AX equals B, versus A inverse times A is this, just the on the ones. So how would we want to solve it? So we would be able to multiply the inverse on this side, on both sides, and this will cancel, and then we will have x equals to our input, or I mean this output, right, or what we have given times this. So we would get our solution if we do this matrix multiplication. So yeah, so the inverse for square matrices, if the determinant is not equals to 0, so 0 is not an eigenvalue, so that means, and also if the rank is full or full rank, that means our row and columns are linear independent. Ax equals 0 is only true for x equals 0. Ax plus b has always a unique solution for every b. So yeah, we have different ways of computing the inverse. So of a 2 by 2, we have a simple formula. We have here 1 over the determinant, which is AD minus CB. And we just flip these two and flip the signs. This would be our A inverse. How we would usually do it is Gaussian elimination. So we start off with our A and identity matrix on one side, and then we turn our A into the identity matrix, and then we would have the inverse on the other side. So yeah. Oh, here I have like numbers, for example. So for the first one, actually this would also work for this. So if we have 1, 1, 2, minus 1, determinant is 1 minus 1 minus 2 times 1 equals minus 3. So A inverse would be minus 1 over 3. And yeah, and here we flipped. So yeah, this will be our inverse. So yeah, if we look at the Gaussian elimination, here we start. We would first delete the last row by taking -2 of the first row. So -2 and then 1. So, or -1 minus 2 equals -3. So here we have a triangle. So we write that here, the -2. And then we divide the last by -3. So here we see divide by -3. So we get 1. And then at last we just need to this row minus this one. So we get like this. So this row minus this one, we will get this. And here we see these two are the same. So both ways work. And what is this one? This one comes from this one. So it's like 1 over the determinant of A, and then the adjacency of A, I think. Is it adjacency? I don't know. Whatever. So if our A is A, D, C, B, or A, B, C, B, A, B, C, D. So basically what it is we always switch the signs, plus, minus, plus, minus, plus, minus, and then here we start minus, plus, minus, plus, and here plus, minus, plus, minus. So you get the gist. We always flip the signs. And then here, so in this cell, we would just remove, or here, we would not look at this row and this column, and we would just take the determinant of here. So yeah, here we would not look at this and this, we would look at the determinant of whatever is in here. It can be bigger. So yeah, and transpose. So yeah, and here we see if we start out with 3 and 0, and then when we multiply it with the inverse, we can see we get 1 and 2, which is our solution 1 and 2. So why don't we always use inverse? Why do we have so many other topics? So because the inverse has, of course, some problems. So let's look at this example. If we have 1, 1, 1, 1.0001, and b is like this. So we see like, you know, maybe like in real life when we measure, we get like small errors, you know, they're like slightly offset, whatever. It can happen in real life. And if we would calculate the inverse of this, we would get huge numbers. So here, yeah, 10,000. And when we try to calculate the solution, we would have to calculate like 10,001 minus times 2 minus 10,000 times 2.001. In the end, we just have 1, 1. So we have like huge numbers, and even though we don't actually need huge numbers, or the solution and the starting point are all like small numbers, right? And this is a problem for the computer because the computer does not use like accurate numbers, or if you know, there are always some rounding issues. Numbers are represented with bits, so especially like decimal places will not be accurate. And if these are huge, we will get like larger errors. Oh, that's what I tried right here. So yeah, the rounding problems, it's very large. And this is because of this condition number, which is this, which is very large, these two. And yeah, this kappa can be also like approximated by the maximum singular value divided by the minimum. So yeah, small errors get magnified. So for this one, it's like this times this. And usually you just want to keep it at 1, or just one of them if possible. So yeah, let's look at different. So here we have the inverse. Why we don't do that, avoid in practice, yeah. Because yeah, it also takes more time, so we can see different methods. So yeah, this is the time and this is the memory that we need. So we have other things that are way faster and use less storage. So if we have a symmetric positive definite, that's why we love it. We can use Cholesky. It's the fastest, most stable. So yeah, it's symmetric positive definite. General square matrices, we can use LU. It's like a lower and upper triangle. Yeah, this is the time. And then if we want numeric stable, and also this for the next one, if we have like, yeah, I'll talk about it later, but yeah, if it's not a square matrix, we can also use QR. SVD if it's ill-conditioned, rank deficient, if we have problems, over determined, whatever, we can use SVD. And this one is also, I like it because you get the most information out of your matrix. But of course, it uses the most computation power in space. So yeah, this was all for square matrices, n times n. And now let's look at, if it's sparse or rectangular, that means if it's like this or like this, matrix, overdetermined, underdetermined systems. So we have the QR, which we already saw. It's to solve the least square problems. Then we also have SVD. Can calculate the pseudo inverse with it. Yeah, and then other things. And then normally, there's also the normal equations, A transpose A equals X. This one, it's fast, but then also the kappa is also A squared, and it's not the most accurate one. So that's why we would prefer like QR or SVD. So yeah, let's look at the first one. If A is positive semi-definite, so this is our problem, AX equals B, we can turn A into two lower triangles, L transpose, and then, so we can turn this into this, and then basically we can do substitution, which would be super easy. So what we will first do is, B with the first one, we get our Y, and once we have the Y, we can substitute and then get our X. So yeah, what does this mean? So let's see. So if this is our lower triangle, here we have our B, it would basically mean the first Y value is just 1 or 2 of this. So 2 of y1 equals to 1, so we directly can get 0.5 is y1. So this is what I mean, why it's so easy. And after we have the y1, we can get y2. And then after we have these two, we can find y3. Yeah, so here you see it. So yeah, how is this Cholesky formula? So on the diagonal, we would have this formula. So whatever was an A minus how it gets affected the other squared. We'll afterwards take a look why it's like this. And then for all the off diagonals, it's this formula. Yeah. So yeah, here would be like how the code would look like. So yeah, it's the square root of whatever was in the A position. So example for here, this minus the L values that we already calculated in the first place, the square root of that. Yeah, actually I have an example here. So what we want to do is we have a matrix and we want to turn it into a lower and upper triangle. And because it's symmetric, positive definite, we see these numbers are the same, 4, 6, 4, 6, so it's symmetric. And when we do a multiplication, you can see it's this times this. So on here it would be a squared, and then for example this cell would be this times this. So yeah, it would be just a times b. Yeah, you get the gist. It's like this. So basically we can see how we get these formulas, and then we just need to think, oh, so a squared is equal to 1, and once we have a, we can find this, we can, or do b, and then we get this, right? You see how it would work. Or I mean, sorry, like if we have a squared, we get, because we only have this number, so this we can calculate what a is, and once we have a, so a is number, and then we have this, so we can find whatever is b, and c and d the same way. And when we calculate this, we don't know e, we want to find e, but because we already have b, because we already have b saved in here, we calculated this, we just have one unknown. Yeah. So yeah, this would be different codes, how it would look like, and how we would use it in Python. Yeah, NumPy has it, or SciP. So here we get our a, and then we can just do 2 times the substitutions, or with this one, just a one-liner. Or actually, it also, like, if you just solve it, it will automatically find the most simplest one, the best one for your case. But here it's if you want to do it, like, want to get your L, for example. So yeah, if it's not positive definite, we can actually do an LDL. So it works for all symmetric matrices. Or one way to also test if it's positive definite is if we try to do Cholesky, and then on a symmetric matrix and it says, oh, there's an error, then we know, oh, it's not positive definite. Yeah. So why does this one not work if it's so positive definite means it has all positive eigenvalues, but here we see we need to take the square root, so it wouldn't work for negative numbers. And LDL means we don't need to do the square root of a because we'll just put whatever is there on the diagonal, and instead and our lower triangle would look like this. It has ones on this. So this will be the scaling of the matrix, and this will be everything what was off diagonal. Or this would be like a transformation. This would scale it and then transform it back. You can think of it like that. So that'd be how the code to calculate it would look like. Yeah. Formula, do I have it? Where do I have sampling Gaussian? Oh, sampling Gaussian is also uses LL. Oh, that's why I have it here. Or did I want to go through this? I mean, it's similar, it's just, no, it's fine. Instead of taking the square root, we just have the sum, or just that minus the sum. That's the influence. So yeah, it's a bit different because you could just do like the same thing from up here and with your ones. If it's in the middle, it means you don't need to take the square root because you times 2 sides, whatever. Yeah. Or just times it by 1, and here it would be like twice. So yeah, why do we love it? So actually, if we have correlation matrices, it's also positive definite. And then if we have a sampling Gaussian, I think, so what we would do is we would sample from normal distribution of 0i, right? Yeah, of 0 and identity matrix. This is super easy. We know how to do that. And then if we have, this is our normal or whatever we want. So we have expectation, so the average, and our covariance matrix. We just need to do like this formula to get our x. So that's how you would do it with this instead of sampling from that. So now let's go to the next one, which is LU decomposition. So it works for general square matrices. It doesn't need to be symmetric. So what would happen? A would be LU or PLU in the general case. P is just a permutation. So we have a lower triangle and an upper triangle. And if, so yeah, so we would like do Gauss on it, and if a pivot is 0, that means we need to swap it, and that's why some of them don't have the LU, but we need PLU. Yeah, and usually we swap for the largest pivot to not have numerical issues. So let's look at, or when we solve it, we would have, say here, LU x equals b, right? We would, or PLU, we would first calculate this, Ly equals b. Because it's a triangle, we can just substitute, we can get y easily. This is upper triangle, so we can get x easily, the same as from LL, pretty much. So yeah, let's look at if our A is this. We start off with the P of identity, L as identity, and our upper triangle as the A. So we see here. So as the first step, we want the biggest pivot on the top. So we switch these two rows, which would be visible here in the permutation matrix. We switch these two rows. And then we can do our operation. So here we record what we do. We minus 0.5 of it. This is right. And here minus 0.5. So we add 2 to it, get the values, get the gist. We swap the rows here. So we turn this again. And then, yeah. And then when swapped, we minus this, which is like 1/15. And then we get this. So here we see in the end, we have a upper triangle and a lower triangle in our permutation matrix. And then we will be able to just do substitution and get our x, or what we were looking for. This is how it would look like in Python. It picks the right solver. Or if you want to really use PLU, you can here LU decomposition, apply this, solve triangular to get your solution. Let's move to the next topic, QR decompositions. So this is can be used for both square matrices and rectangular ones. It's numerically stable. It's used for least squares. And where orthogonality is needed. So what does this mean? We would turn A into QR, where Q is an orthogonal matrix. That means it just turns it, does not scale it, so the angles are kept. And then we have a upper triangle matrix for us to easily solve. So yeah, when we solve it. So yeah, it works for overdetermined. It solves the least square problem, minimizes it. Yeah, it's used for linear regression. So yeah, machine learning. And it's also used for eigenvalue algorithms. So yeah, for example, short decomposition uses QR multiple times. So how would we solve it? A turns to QR. We would just times the Q transpose on both sides. That will cancel it out because yeah, Q transpose is Q minus 1. And then here, so we get this value, whatever this is. And because this is a triangle matrix, we can do substitution again, so we can easily solve it. And because Q is orthogonal, that means it doesn't change the angle of B. So if B looks like this, we would just spin it. Actually, I have a animation of it, I think. Yeah, later on. So how do we compute QR? We have different methods. So first we have Gram-Schmidt, we have householder, and then given rotation. So let's first look at the modified Gram-Schmidt. Gram-Schmidt is to find orthonormal basis of vectors. This is the formula. So yeah, basically we take a vector and then we remove whatever appears before. So here we take the dot product, so how much it aligns with the vectors we already found. And yeah, and then in the end we normalize it. So this is just this divided by how much it scales. So it gets into a unit vector. So it's just like a size of 1, or the eigenvalue is 1. So yeah, let's look at this. So if A is this, so we have V1, V2, V3 as the starting point. So yeah, when you first calculate the first one, so here we see this formula. What should I call this? Prime. It's just V1. We don't have any W yet. So W is what we get in the end. This is our first one, so we don't have anything else. Okay, V1, we calculate the norm. So the size of it, it's just H times squared and then taking the root. So yeah, it would be 1 over square root of 2 of this. So this would be our first vector. And then we try to calculate W2. So we would take V2 and then minus the influence, or minus the direction in W1. So we take the dot product of V2 with W1 and times W1. So here we have, yeah, so this is also like R12. So here we would take the dot product, this and this, yeah, so 1 over square root of 2. So yeah, what this means is basically we have V2, and this could be like, for example, W1, and this is, for example, it's just like 1 over square root of 2 along this side. So the orthogonal component, which this one cannot do, is in this direction, right? So we're trying to find something that's orthogonal to this vector. So we would minus that one, so this would be our second W2 prime. So we need to normalize it. We find it's this. So yeah. Same thing. I'll just be fast. We need from 1, 3, 2, 3. Just the same thing as above. We minus V1, V2, or W1, W2. of this component, and then we get this. Okay, we normalize it. So yeah, and then we can put it together. W1, W2, W3 is our Q, and then our R vector is made up of these values. So all the norms here. So we just fill that in, and we get our upper triangle. So yeah, it's easy to solve. QR x equals B, we would take Q transposed, and we get Rx. So this would be easy to solve. So we first solve whatever's QTB, we get Y, and this value can do substitution again. So let's, I didn't write here, but I think I have a, do I have one? Oh no, I don't have. But for the next one we have. So householder, what is this? It's reflection matrices. So we use reflections to zero out entries below the diagonal. And reflections are orthogonal and numerical stable. So this is our householder matrix, or how we would calculate it. And we see that Hx does not influence x, the size of it. So yeah, that's what I'm trying to say. It's just keeps the size. Yeah. So if we have like x, we would just put the distance along the one of the bases. So yeah, we started with this. We have this A, and in the end, we want to have an upper triangle. That means for the first column, we only want a number on the first space, and so we need to make the other two 0, 0. And we can find this x, or what is it? The norm of this square root of 2. So yeah, we take alpha as negative, the norm, and then our v vector is x minus, so our v vector is x minus this. So yeah, x minus this one. So it's like, so we would have like x is like this, right? Or how can I draw this better? So yeah, let's see. So if let me put it like this. So it will mean x, let me copy this. So what this means is we have x, and then we do minus this. So that means we go up here, and then we move back, and that should be the same as our v. So that we will get our v. So this is like this, right? So we see x minus this x norm times E1 equals our v. This is what this formula is, basically. And then we can compute our householder matrix 1 with this formula. Yeah, if we do VTV, it's equal to this, and VVT is equal to this matrix. So our householder would look something like this. So we can see. And then we apply householder to A, and then we would get our A prime, which looks like this. So we removed the first, or the two numbers below the diagonal, and now we can look at here. So now we want this to also be equals to 0, so this needs to be equals to 0. And to do that, we can just look at this. So this, the norm of it is square root of 3/2. So we take this minus 3/2 square root. So the same thing again, we calculate V2, we calculate these two numbers, and then we can make our H2, or the H2 tilde. Our householder matrix is this number, and to get our H2, we just have one on the diagonal and fill out this with H. So it would look like this. And then we get our R when we apply H2 to the A that we got here. So you could see now it turned into triangular, and our Q is just H2, H1. So what we did is basically R is, if we apply H1 and H2 to A. So it would look like this, the Q. You can use Python script to visualize it. Actually, first go through this. When we solve it, yeah, we do Q. So yeah, we know the Q, right? We know the R's. So we do Q transposed, and then we can just do the two substitutions. I already did that. So let's look at what this actually means visually. Let me switch back. Actually, this one's smaller. Where is it? Householder. So here we have the same matrix, 1, 1, 0. So yeah. I need to remember again. What was what? So I think this was, oh yeah. B is where we want to get. And is it? Wait, let me just apply it. So we can see this is what we originally have, and then I didn't write it down, but yeah, we would apply H1 to it, and hopefully one of it moves to the axis. That means the two numbers, if the two numbers are gone below, if it's 0, 0, then it means it only has a number along the x-axis. So when we apply, you can see if we do H1, we would move the blue, the light blue one basically, to the axis. So it's like a bit hard to see. But yeah, it gets like rotated to the x-axis. Now if we do H2, we would do like a rotation, and it will move it to the xy plane. Let's see that again, actually. Let's see. So it was initially here, so if we apply H1, it will just like rotate to there. And if we apply H2, it would rotate this down here. And then we can apply Qt to B. So we would also, so that's how when we solve it, when we apply to Qt to B, it will be here, right? So our B would then look like this, and then we can just solve using substitution. So we see R, this is R that we have, right? So 1.15 of x needs to equal to 0.577. So what is that? X is 0.5. So here we see that's the right solution. So it's basically how we would solve it. So we would like rotate the matrix to be aligned to these axes. One axis, one plane, and one can be free. And then, yeah, we rotate B to the right axis so that we can just solve. So yeah, let's look at the next one. How else can we calculate our QR decomposition? We can do a Givens rotation. What is a Givens rotation? It's basically 2D rotation to make one entry 0. And then we repeat it for all subdiagonals. A Givens rotation looks like this. It's one on the diagonal, and then we have whatever we want to rotate. It could be also here. we have the cosine, sine, and the negative sign. So yeah, what this does, it basically just like does a rotation. So we have AB, we get R and 0. And this is how we can calculate. So yeah, let's look at this matrix again, the same one. We want to turn this to 0, so we rotate these two. So first we calculate R, which is again this right here, yeah, you see, right? R is that, and then how much S and C would be, sine and cosine. So R is this, and the C is A divided by R, which would be this, and the sine is minus B divided by R. You can think of it as the unit circle to get this formula. Yeah, so our first given rotation would look like this: cosine, sine. And then when we apply that to A, we would see that, yeah, here it also gets 0 out, and here we get square root of 2. And then this is our A1. And then we look at, so the next thing we want to 0 out is this. So yeah, if we have like 3 things here, we could do like 1 rotation to 0 out this one, and then 1 rotation for this and this row. So yeah, here again, we do that, we get our second given rotation. If we apply this, we get our R, and our Q is made of, similar as before, right, from the different rotations multiplied with each other. So yeah, again, I have a script to visualize what happens. So here with Gibbons rotation. So here we start out again with our first matrix, our matrix. So we would apply G1. So it's like a rotation. We see it turns one values to 0. So it means, yeah, turns it to this. Because it's already 0, maybe I should have done with a different example, but yeah, this rotation will make the Z to 0, which it already is, and then G3 would make Z to 0, so this part to 0. So we turn it down, and then we see here it got 0. So now we got a triangular matrix. Oh, actually, and then we also need to apply it to Q. Did I apply to Q? I forgot. Yeah, I did, I think. Well, reset. Well, I forgot when I wrote this script what I did. Okay, let's apply out. So yeah, here we see again, we first rotate. Oh, I'm already applying Q to B as well. We see how B also rotates with it. So we actually also do the rotation on B, right? That happens when what we do QT is basically G1, G2, G3. And now we can just solve it. We again get this, right? Oh, we see like the R matrix is almost the same as the last one, just that the signs are different, but yeah. So the idea is we do a rotation that doesn't change angle or scaling, right? And then turn it into a triangle so we can easily solve. Let's move back. So yeah, we already saw that. Did I not want to talk more about QR? Whatever. So let's move on to the next one. We got our singular value decomposition. This is pretty important. So yeah, it works for ill-conditioned systems or rank-deficient systems, also for overdetermined or undetermined systems. What does this mean? We have an A that's m times n, and then we would get a u that's mm, a v that's nn, and a diagonal matrix which has the original size of n times n, and then we can write a as in this. And this is an orthogonal change of bases, axis aligned scaling, and then another orthogonal change of bases. So what this means is we would rotate it for all the, is it eigenvalue? Well, the eigenvectors of A transpose A that it aligns to x equals 1, to our normal xyz bases. And then we do the scaling. So in each eigenvector direction, we scale it, and then we rotate it into the solution space, so the output space. So yeah, this is the singular values are the square of the singular values are the eigenvalues of A transpose A. Yeah, and why do we do this? A transpose A is symmetric positive semi-definite. That means all eigenvalues are greater or equals to 0. That means, yeah, we can do eigen decompositions or orthogonal decompositions. Well, it comes afterwards in the properties or in the special matrices when I talk more about positive semi-definite matrices or symmetric positive definite. And yeah, once we do that, we get SVD, we get our, if the matrix was already symmetric and we do SVD, then we get the eigen decomposition. So we have eigenvectors with eigenvalues. And if it's positive, it's the same. If not, it's the what is it called? The value. The positive value. Oh, I forgot. Why am I forgetting things? It's a bit late. I've been talking long. The absolute value. Okay. So yeah, what can we do with it? We can calculate the more Penrose pseudo-inverse, which is basically the diagonal is 1 over the singular values. Oh yeah, and one thing is here, the diagonal has the singular values from the largest to the smallest one. And yeah, here we just do the inverse of it, so 1 over the singular values. And if we do this, it's the pseudo-inverse. So what did I want to show here? Oh, here it is what this is, right? If we have A times V, I see. So if we have A and then times the input eigenvector, we would have the scaled value of the output of UI. The output that we'll see a bit more later on that. So why is this? Because we apply V on this side. So if A is this, right? If A is this, we apply V on this side. It's the identity, and then we would here have our singular values. So yeah, we see that singular values times the U vector, the output space vector. That's why this is valid. This is the definition of what U and V are. So then we see A transpose times A would look like this, and because this is the inverse, so AS squared, so the singular value squared. So that's why we take the square root. Yeah, blah, blah, blah. And yeah, we can do, with this, we can do low rank approximations. So we don't want all, what does it mean? We want to compress data, or, you know how eigenvalues is how much the matrix affects our input in certain directions. And if the eigenvalue is small, it has very little impact. That means if we want, we can like ignore it. What if we ignore it? If we just use the, for example, the 3 most largest eigenvalues or singular values, the 3 directions that scales the most. So we can save space with that, make it simpler, whatever. You have like different places you would use that machine learning to use less features. That's why we love this. So yeah, the properties is the column. What did I have here? Column space. Oh yeah, column space is the span of the first R columns in U. The row space is the span of the first R columns in V. The null space is the columns where V or singular values equals to 0. So R is basically where all the singular values are not zero. Left null space is the columns of U corresponding to singular values equals to 0. I think we'll look at it later more, right? I believe I did something. Yeah, vector space, I talk more about that. So how do we compute this? So we do either ATA or AA transformed, depending on which is easier, or usually whatever is smaller is easier, maybe larger can be easier, but whatever. And then we calculate the eigenvalues of this. That means the determinant of this minus lambda identity equals to 0. And then with that, we calculate the singular values, which is just the square root of it, and then sort it from large to small. And then we can compute the right singular vectors with this formula. So it's like the eigenvectors of A transposed A. And we normalize it. It's orthonormal. So yeah, it's orthonormal V. So what this means is maybe we need to orthogonal. Wait, so with this we get the U, right? And then we can calculate, V, and then with this, with the V, we can calculate the U with this formula, because A times V per definition, A times V should be equal to the singular value times U. That means we just want to divide by singular value, so U should be this. Let's look at an example so you know more what it does. So we take A transpose times A, we get this. We find the eigenvalues of this. So we do minus lambda, we get our characteristic polynomial. We solve it for 0, and then we see we have 6 and 1. So we have 1 minus 7 plus 6 equals 0. So we know, yeah, these are the eigenvalues. We sort it by size. Sigma 1 is square root of 6 and 1. Now let's find for the eigenvalue 6, what is the eigenvector of it? So we do this, ATA minus 6 identity, so here minus 6, so it's built just like 5 minus 6, 2 minus 6. Look at this, equals to 0. So when is this true? It's then when v1 is 2, 1. So yeah, what does this mean? 2 negative 1 equals 2, right? So if we move 2x minus 1 times minus 1, so minus 2x equals 2y, right? So it will be the same, right? And 2x, this is like, if we move it to this side, it would turn from minus 4 to 4, right? So it's like 2 to 4, it's 2 to 1. What is the norm of it? As in the size of it, the length of it, square root of 5. So yeah, our v1, we normalized it to 1 over square root of 5 of 2, 1. So we do the same for lambda equals 1. We would get this vector. So we get our v is just v1, v2, which is this. And now we solve for u1. So for the first one, so for sigma is square root of 6. Our vector, corresponding vector is this one, 2, 1. This one, 6. So our u is 1 over singular value times a. Is it times? Oh my gosh, I'm getting tired. Yeah, times our a and then our v1. When we do this, we can get this as the solution. So this is our u1. We do the same for u2. And because a is 3 times 2, our v was only 2 times 2. So now we need something that's 3 times 3, right? Wait, I'm getting it wrong. Oh, because I have it on the wrong side, right? Because it's UAV. Yeah, it's UAV. Where did it go? Here. So our A is 3 times 2 times 3, whatever. And our 2 times 2. So now we need a 3 times 3. So we see this multiplication will be correct. Yeah, because A is 3 times 2, we need one more U. So how do we get this U? It needs to be orthogonal to U1 and U2. So we can either use Gram-Schmidt, which gives us an orthogonal vector to those two, or we take the cross product, which is going to be perpendicular to those two. So we can just do U1 cross U2. If we do that, we get this vector. I think it's normalized because both are normalized already. And then we can build our U. So this would be U1, U2, U3. And then our diagonal, because it's longer, so we have a 0 row, but the singular values go on the diagonal. We have our V, and then with this we can basically solve it. AX equals B is basically this. So if we apply UT on both sides, it would be cancel out this one, right? And then we would do the inverse of the diagonal, which is E plus, right? And then times V, so V on this side will cancel out this. So that's how we get the pseudo inverse. So yeah, X is pseudo inverse times B. Yeah. So yeah, let's look at another script. This is the last one. Where do I have it? SVD. So what does it mean? So these are our two the eigenvectors of A transposed A. So it's basically how our input space, the eigenbasis of our input space, singular vectors. So what we do is basically we try to move them to align to our axes, x and y, and then when we're there, we can then scale it and then move to our output space. So let's see that in action. This is the start of x. So this is B where we want to get. So we would first spin it. So this is applying our V, I think. So we see V1 and V2 are aligned. So this is what best describes our input space. And the next, we scale it with the two singular values. And then we rotate to the best basis that describes the output space. And then we can see we arrived at our B. Basically, this is what... So it's basically like from x, from the start, if we apply A, we would get here. But through the singular value decomposition, we turn it into 3 steps. We first rotate, scale, and then rotate. And then we get the same thing if we do it in 1 step. But yeah, with this, we can calculate solutions. This is how it looks. Maybe for the animation at the start, I'll do this. So yeah, it's pretty helps you understand what singular value decomposition actually is, because when I learned it, I think I didn't get the... I knew it's about like eigenvectors and scaling them and rotation, but I didn't know it aligned them to the basis. Oh, switch back. So let's look at vector spaces. So column space is the output space, Rm. So what outputs A can produce? Here I'll go through. Row space is the input space. So it's N. M is how many variables, right? X, Y, Z, how many unknowns we have. So it's the size of the column. And row space is the size of row, right? How many functions we had, whatever equations we had. So it's input space, which input direction actually affects outputs. Oh my gosh, it's getting hard to speak. I need some water. Let me do a quick water break. Okay. The null space is input space, but the inputs which get killed or cancelled out, the left null space lives in the output space, and it's which outputs are impossible to reach or unobservable in control systems, I guess. So yeah, n is our unknown variables, m is the equations. So let's look at what SVD did, because there we can see it like, it's a good example, or it exactly describes this. So we have our input x, vt gives us to the input coordinates, and then we scale the modes, and then u would give it into our output coordinates, b. So we see v is like this, vt is like this, our singular values, and our u saved like this. So when we have output B, how do I explain this? How do I see this the best way? Well, let's start from here. This is how it would be multiplied with each other, right? So if this is our input, x, y, z, this one would describe our first equations, right? This times this, so this times this, plus this times this, plus this times this, it would give us to x1. So it would give us the input, it would like in the best way, or our optimal input would be like, yeah, in the x prime. And if the row space is those where it's non-zero. So here we see in the end this times this times this, and then 0 times this. And 0, that means this, whatever was here, we will just ignore it. So this is our null space. That means this, the last input, which is formed by both x, y, z, right? It's a bit hard to understand at first, but theoretically, because we use this later on to calculate, so this can be seen as the input. So it's like the best input x, y, z. It's not anymore x, y, z, but it's in a different spaces. But the last one will be ignored, so that's our null space. Or you can think of it, the eigenvector, which has an eigenvalue of 0. With this, we scale it. We would have, so this is basically just this times this times this. So we scale and the input, and then we have the u, which transform it into our output space. So this is like our input, right? And these are the equations. So U describes which B's are achievable. So in this, so every column would describe, for example, a vector, right? So for example, this, we can, if this and this are achievable, we can achieve every point on the plane. So if it's like 3D, if we only have these two vectors, u1 and u2 in the column space, only whatever is on the plane is achievable. We can only move this direction, but we cannot move up. So this describes the relationship between x, y, z, or the inputs. And so this means whatever is here, the left null space, this direction is not achievable. So and that's how we get our B, this times this. So yeah, our rank is R. R is the rank of A, which is how many singular values, active directions, and for all singular values equal to 0 is where the direction gets killed. And in control systems, we have equations like this, right? It can be controllable versus uncontrollable, observable and unobservable can be the equivalent of this. Yeah, that's why we also use SVD in control systems, because then we can see like how much each is like controlled. Do I have a animation for this? I forgot. Whatever. I thought I had something more that I wanted to say, but currently forgot what it was. Maybe I'll remember it later. So, vector space definition. So what is a vector space? It needs to be x plus y equals y plus x. I keep on forgetting the names. Communicative. I don't know. Whatever. But yeah. So yeah, we can use the brackets. It should be the same. We have a 0 element that's inside the vector space. So we have x, any vector plus 0 should give us x. We need an x where we can have a minus x where it equals a 0 element. If we like scale it, should be like this, you know, and just different rules that apply. So this needs to apply for it to be a vector space. It could be like crazy, but it could be anything, but as long as it fulfills these rules, it's a vector space. The properties that it has: if a plus b equals a, then b must equal to 0. Yeah, a times 0 is 0. 0 times a vector must equal to 0. Minus 1 times a vector needs to equal the minus of itself. So yeah, let's look at what norms is. Norm assigns a non-negative length to a vector in a vector space. So basically measures the vector length. And the most known is the second norm, the Euclidean norm. Actually, look, the norm is always larger than 0, equals or larger than 0. If it's 0, then it means the vector itself is 0. We can take out this, would be like this. Take out a scalar. The norm of two vectors, so this plus this, is always smaller. So this plus this, right? The distance is always smaller than this plus these two, right? It's simple geometry. Yeah, we have that. Oh my gosh. Euclidean norm, which is the square root of all the things squared. Can be written like this. We have different norms. If it's infinity, then it's just whatever the maximum is, or p is. Yeah, well, you get the gist. Inner product is defined like this. We have linearity. AU plus BV dot product with W is A times dot product of UW plus B, BW, or beta, alpha beta. It needs to be symmetric. UV equals UBU. It's positive definiteness. It's always larger than 0 or 0 if it's 0. So it measures how aligned two vectors are, and we can also get the cosine or the angle between the two vectors with this formula. The dot product divided by length of the two. So we can see, so if we have the unit circle, so if we want to see how aligned these two are, it's right, it's this UV is how aligned is UV, and I mean the cosine of this gives us this length, right? The cosine of this is basically this divided by, I forgot, whatever, I forgot what I wanted to try. I wanted to like, I mean, you get it probably. I'm just too tired to explain. Or actually, yeah, on the unit circle you see, because this is 1, so it's divided by 1, right? And the cosine of this is this divided by 1, right? So yeah, the cosine gives us this. So the cosine of this basically gives us the length, and because this is on the unit circle, this is 1, so it gives us this length. So you see. So yeah, the dot product is like this, U transpose times V. Usually you can have like weighted dot products. if something is orthogonal, if u and v are orthogonal, then it equals 0. So yeah, if it's like this, then they don't influence each other. 0. So this projected on this is 0. This yeah, whatever. So it's basically projection. So this and this. So it's basically if you project this on here, you would have this, or if you project this on this. Yeah. What is this? Orthogonal basis is, it's just a definition of orthogonal basis. It's always 0, the dot products, if it's not equal to each other. For functions, f and g, you would just take the integral of this, give you the dot product. Now, let's move to some properties of matrices. We have orthogonal. That means it's perpendicular or independent from each other. So yeah, that means the dot product equals 0, or if you take for the functions it's equal to 0, that means they're uncorrelated, and that means q transpose q equals I. When that is true, it's orthonormal. So orthogonal, and it doesn't scale. Yeah, and this orthonormal preserves length and angles when we apply a transformation. So like before the QR transformation, it preserves the length and angle. It just does a rotation in some sort. Determinant of a matrix. So determinant is volume scaling factor of the linear map. So how much scales after the transformation. Determinant of AB is that's A, that's B, times that. So from transpose, it's the same. From identity, it's 1 because it doesn't change anything. If A is orthogonal, orthonormal, then the determinant is plus minus 1. If we have a factor, a scale A, scalar times A, and if we take it out, then scalar needs to be to the power of n. Yeah. If we swap rows from A, then the determinant will be multiplied by minus 1. A is invertible if determinant of A is not equal to 0, and of course if it's square. And yeah, the determinant of inverse of A is determinant of A inverse, or to the power of -1, which is, and A to the power of A inverse is 1 over determinant of A and adjacency of A, which we already saw. In combination with, or in regards to the eigenvalues, the determinant A is just the multiplication of all the lambdas, because if you think about it, if we have the eigenvectors, if this scales by 2, actually I can have an animation, this scales by 1, for example, it stays the same, then in the end our volume scales by 2, or if it's 2 times 2, then it's, 2 times 2, it's 4. The volume increases by 4. If one side times 2 and the other side times 2, it's times 4. Yeah, and that's why it's this. It's 2 singular values. The determinant of A, the positive. So, I'm tired. So if we multiply all the singular values, it's the, I forgot the word again. Yeah, it's determinant of A. If we take the exponential, determinant of e to the power of A is e trace of A. Trace is just the addition of the eigenvalues. If we take the logarithm, it turns to trace of log a. If a is positive definite, because if not, the logarithm is not defined. Calculations. What did I do here? Oh, how do we calculate eigen? Oh, how do we calculate the determinant? So we could do Gauss or LU. So sign of row swaps. So we just remember how many times the row gets swapped. And then we just multiply all the values on the diagonal. So yeah, it's basically all the values on the diagonal times the row swaps. We do Gauss LU. We could do eigendecomposition for symmetric diagonal. That means it's diagonalizable matrices. So we turn A into Q, a diagonal matrix Q. Then the determinant of A is just the determinant of this diagonal, which is just multiplying all the eigenvalues. If we have a block triangular, the determinant of A is just the determinant of the blocks on the diagonal. Maybe it makes your calculations easier, then you can use this rule. There's the matrix determinant lemma, so that A plus UV transpose equals to this, so it's basically when we want to update an A, we can easily find it. Why do we use it? I forgot. It's this formula anyways. Yeah, when we want to update a matrix. Block determinant, Schur complement. It's used for probability, or we have the same formula. We have A, B, C, D. If A is invertible, then the determinant of M is determinant of A times this, the Schur complement, I think. And then probability, we have the covariance of x2 if we have x1 is this formula, so we see it's the same as this. It's basically how much is this been affected by x1, so we remove that and then multiply it. If we have a 2 by 2 matrix, it's simple, it's AD minus CB. And then this, I like using this to calculate, it's the Laplace. So this is the signs again, plus, minus, and then we always like switch signs. And then when we calculate the determinant, it's basically A1 times whatever is in here. So when we look at this, so we take the first element and then we disregard whatever is on the same line and row, and we times the determinant of this block, whatever is left over. And then with the signs, the next one, this is minus, right? So we not look at this and not look at this, and then we have the determinant of whatever is in here. So if we do this, we can also get our determinant. So from this, let's move on to eigenvalues and eigenvectors. I've already been talking about this. One of the most important topics in linear algebra. So what is the definition? If we have a to the eigenvector, it's just the same eigenvector, but just scaled. What it means is if we have in one direction, we apply a, our solution or our output is just it scaled by a factor, which is the eigenvalue. And this also means a minus lambda I times v equals 0 if lambda is an eigenvalue. That means determinant of that is 0. Later we have an animation where I can actually show you. Actually, let me show you this right now. Or actually after I do the calculations. Maybe better. So eigenvectors are directions that A simply scales by eigenvalues, by a factor. So the determinant of A is just the multiplication of all the eigenvalues. The trace is the sum of the eigenvalues. If A is already a triangular matrix, then the eigenvalues are just the diagonal entries. If a different matrix is just a transformation of A with this, it has the same eigenvalues. If A is real and has complex eigenvalues, then the minus of it is also an eigenvalue of it. Then it comes in pairs, basically what it means. If A is symmetric, we can make a decomposition. Right. Why do I have it here? Which is Q. Yeah, if it's a symmetric, then we can do a decomposition. If it's a normal matrix, why do I have this here? I don't know. Yeah, and the singular value decomposition, the singular values are just the positive numbers of the eigenvalues and square root. Well, if A is normal and diagonal, okay, then it's just the positive values of the eigenvalues. And if it's positive definite, then it is the eigenvalues, the singular values. Now I'm gonna eat and continue later. So welcome back. I got finished dinner. So let's continue. And let me give a quick recap on everything that we did. We went through, what linear systems are, some operations. We saw how to solve for AX equals B, how to get our solutions, some different ways of solving it. And Cholesky for positive, definite, symmetric matrices, LU decomposition for square matrices, QR decomposition if we want it to be stable numerically, and also for rectangular matrices via the householder, Gibbons rotation, and where was it? Gram-Schmidt. Then we also saw singular value decomposition and what each of the matrices mean here. And we also saw the vector spaces. We defined norms, inner products. We saw what orthogonality means, what a determinant means for vectors. And now we arrived at eigenvalues and eigenvectors. We saw some of the properties, and now let's go into computation. So the first way to do it would be using the characteristic polynomial. So how do we get that? What we do is the determinant of A minus lambda, the identity, equals 0. And why is that? Because let's say A has an eigenvalue, which if it's 1, and then let's say it stretches it by 2. So in the end, so we have one direction that has the size of 2, right? And if we minus an eigenvalue, so if we minus equally 2, that means that for one direction, it would be 0, because we from 1, we times 2, and then we minus 2. Just as an example to see where it's coming from. Let's go with this matrix. Then we would do minus lambda on the diagonal of every entry, and then we would write down the determinant or the polynomial for this. We get a equation. I mean, there are different ways to guess what the eigenvalues are. For example, the trace is the sum of the eigenvalues. So we see it's 6. So it's I mean, you could also like calculate the determinant of this, but I didn't do that. But then you can see what all the numbers multiplied should be, and then you can like guess one of the eigenvalues, and then you can divide it, and then you can get your equation. Or you just, if it's quadratic, you can just use the midnight formula or ABC or whatever it's called. So yeah, so we see we have eigenvalues of 1, 2, and 3, and there's an algebraic multiplicity. That means how often does an eigenvalue appear, and in this case all 3 of them only have once. For example, if like one of the eigenvalues 2 would appear twice, then it has an algebraic multiplicity of 2. In this case it's just 1, and then for each of the eigenvalue we would do a minus the eigenvalue times identity, and then we would see or solve that and see which vector like fulfills this. So if we put it in, it's like if we have like the axis of x, y, z, then we would have here minus the first variable plus 6 of the last one, and then we like try to solve this. We see that we get like y equals minus 5z. That means if we just set z as 1, then y is minus 5, and 6 x would be 6. So in this case we can freely choose one variable. So I would just choose like the easiest, like 1, and then the rest, fill out the rest. We do the same for the other 2, and then we get the other 2 vectors. So yeah, then there's also geometric multiplicity of an eigenvalue. So it's the dimension of the eigenspace of this. So it's basically how many eigenvectors do we have for that eigenvalue. So in this case, it's because we only have one eigenvalue. We only have one eigenvector, but let's say, for example, think here. In this example, we would have 2 times like 2 as lambda. So the algebraic would be 2 for 2. And then if we try to find an eigenvector, we get to this. We see like x3 equals 0. That means we can freely choose x1 and x2. So for example, we can just use this. It's just need to fulfill this condition that x3 equals to 0, and then we see the geometric multiplicity is 2. But let's say if we have this one, it would say x2 equals to 0, x3 equals to 0, and then 0 equals 0. That means we have x1. x1 is the only variable that doesn't appear, so we don't have any constraint for that though. So we can only freely choose that. So we have a geometric multiplicity of 1. So we only have one eigenvector for this eigenvalue. But yeah, in this case, we have 3, and we have 3 vectors. So yeah, Yeah. And if the algebraic is equal to the geometric, then A is diagonalizable. Oh, I have a spelling mistake here. Oh, whatever. I'll do that later. So yeah, we can write it in this form. And then it's also called an easy matrix. Now we have another way to find that, and that's through the Schur decomposition. So for square matrices, there exists an orthogonal Q and a quasi upper triangle such that A equals Q the upper triangle and Q transposed. And in this case, the eigenvalues are on the diagonal, or almost equal to the values on the diagonal. And if A is normal, that means symmetric, then T is diagonal. And yeah, of course, with this easier matrix exponential, matrix function, Lyapunov, log. It's nice so we have this to calculate, because of f of A, we can like do like two matrices and then just f of the diagonal. The triangle. And how do we do Schur? We basically use QR multiple times to get to this equation. Basically, it's at first A is a 0, and then we do a QR decomposition, and then so that's QR, right? And then we multiply R and Q. That would be our next A, and then we do the QR decomposition of this new RQ, and then after a few iterations, it should converge to Schur, or at least the eigenvalues will be on the diagonal. What did I have right here? Oh yeah, let's look at a characteristic polynomial. Let me see this. What else do I have here? I got like Schur decomposition. I mean, the code you saw, it's, yeah, on my iPad as well. So let's do this. So characteristic polynomial, basically, what did I want to show you? Oh, so let's say this is your matrix. So here I have plotted, I think, the eigenvectors. And if we minus, and here I can like choose lambda. So if we minus, we can see if we reach, which did I, oh yeah, I took the first one, which will have like the eigenvalues of 1.7, so the first example of the very beginning. So yeah, so from here we can see the matrix, so it does this, right? So this was the first matrix. Basically, it scales the eigenvector by 1.7, and in this direction by minus 1.7. So here we multiply by 1.7, and let's say if we minus 1.7, we can see then one of the dimensions goes to 0, and then our determinant will be 0 as well. So that's why the function works like that, or that's how we find the eigenvalues and eigenvectors. Yeah. Let's get back. Okay. So now let's look at some special matrices. Start out with a square. It's n times n. The input and output are in the same space. Yeah, so we can do the first few decompositions, the LU decomposition, which is fast. So let's say we have a symmetric. That means A transpose equals A. That means it's diagonalizable. It has real eigenvalues. So we can do eigendecomposition. We can do LL, Cholesky, LDL. Oh, LL only if it's positive definite, but we can do LDL. So yeah, it has real eigenvalues. So we can find orthogonal eigenvectors with diagonal eigenvalues. We can do spectral decomposition. We can, so the singular value decomposition gives us the eigen decomposition with the singular values equals the positive of the eigenvalues. Why do I keep forgetting it? Yeah, and then we can easily apply functions to matrices. So it would just look like this. So we have our orthogonal, and then f applies to the diagonal. The inverse is very easy to calculate, which is inverse the diagonal. We can do low rank approximations because if we know the eigenvalues, we just keep the eigenvalues that we want and the eigenvectors. Yeah, there's the Sylvester's law of inertia. That means the amount of positive, negative, and zero eigenvalues stay the same if we have like similar matrices. That means just multiplying on each side with S, and let's transpose. The powers are easier to calculate because we can just use the power on the diagonal. Yeah, and if it's positive semi-definite, we can do Cholesky decomposition. Yeah, covariance matrices are an example for this. Graph, Laplacian, Hessians, and optimization. We also look for that. And in this case, the singular value decomposition gives us the eigen decomposition. Yeah, and square roots are easy to calculate. Yeah. So next up is a normal matrix. And that means if A transpose A is equal to A transpose. And that means we can find an orthogonal eigenbasis for the matrix. So yeah, the cases are if it's Hermitian, or symmetric. If it's unitary, the eigenvalues are in the unit circle. If it's skew-symmetric, then when A is equal to A transpose is equal to minus A, so the eigenvalues are pure imaginary, then it's like a rotation matrix. If it's diagonal, it's normal. Yeah, if it's a rotation matrix, complex diagonals, it's normal. Yeah. And yeah, so if it's normal, we can do this decomposition into orthogonal eigenbases. SVD is the positive values of the eigenvalues. A to the power of k is normal, and yeah, and the Hermitian of A is like this. Yeah, and the Shor decomposition will give us a diagonal matrix. And next up, let's look at orthogonal unitary matrices. What does that mean? It means Q transpose Q is equal to identity, so the transpose itself is its inverse. What does it mean? It's norm preserving, it doesn't change size. Determinant, or basically it also means the determinant is 1 or minus 1. Eigenvalues are on the unit circle. The condition number is 1. So yeah, preserves length and orthogonality. So we saw the cases are householder matrices, which we saw, Gibbons rotation, or orthogonal product of reflectors or rotations. And then what was here? Cayley transforms because of skew-symmetric A. Orthogonal. Oh, if it's skew-symmetric A, then we can do this, and we would get an orthogonal, I think. Yeah. That only works if it's not minus 1. And then we can approximate e to the power of a is identity minus half a plus identity plus half a inverse. So it comes from here. Approximate of exponent. Can do yeah, it's I plus a plus half a, so it's the Taylor expansion. So Padé approximation. Where's the word this came from? Oh, this is where this came from. So this came from this. But yeah. Triangular matrices. So the eigenvalues are on the diagonal. The determinant is just the multiplication of those. And it's an easy exponential. That's why we love it, and easy to solve. Invertibility, if all the diagonals have non-zero, that means the determinant is non-zero, so we can inverse. And the inverse is also triangular. So if we do addition or multiplication, it stays triangular. T transpose switches from upper to lower. And we only need to do forward and backward substitution to solve for x, which is perfect. Yeah, and the log that is just the sum of the logarithm of the diagonal. And then we do exponents. It's also easy because I think this needs to apply. And then we can calculate, so if this equals this, then we have this formula where we can find the exponents, or easily find what e to the power of t is through the formula. So yeah, basically we could like write down, for example, if we, so on the diagonal, it's e to the power of lambda, or whatever was on the diagonal. And then we just need to find these values, and we can do that if we, let's see, for example, e2, if we do this and this, it needs to be the same as this, so we can write down an equation and then solve for it, solve for e, and it can be written down as this formula. Basically the diagonal is the e to the power of diagonals, and then the off diagonal, let's say this one we can see is ik. This was triangle. So let's say we want this value, then it is whatever was in here, e to the power of that minus. So the original value a times whatever was above and below, and then we add this value, which is, yeah, whatever is between. So if we're just here, we just have these two, but let's say we're here, if we want to calculate this, then we also have to consider these two. Yeah, just go through the indexes. So it's always, it starts, let's say I is smaller than k, so let's say 1, 3. So this will go, it will go to 2, 2, or no, 2, 3, or like 1, 2, 2, 3, minus whatever. Just put it in and you'll get the right thing. There's also a decomposition trick that we can do. So the triangular, we can split it to a diagonal and a nilpotent matrix. So yeah, so we would just, do I not have an example? Here, like we split it. So we split it to only having the diagonals and then plus whatever is on the off diagonals, because the eigenvalues are 0, so that means it's nilpotent. And if this is not always the case, but dn and d, if it's commutative or if it's equals the same, then we can do this. So we take this to the power, we can use this formula, or you just have power this and then can calculate it, because n to the power of some number will equal to 0, so we only have a finite of matrices that we need to calculate. For example, in here 2, 2, it's like 2 times the identity, so we're like I always forget the word, but yeah, it works for any matrices. So yeah, we can write it like this. So we do this, it's, yeah, we can write it like this, and we know n squared, so this squared is equals to 0, so we don't need to calculate anything else. So we just need to calculate this, so it's like easy to calculate. So even if it's like high power, it could be 100, we can easily find a solution. Yeah, the Jordan normal form would look like this. We have lambdas on the diagonal and then ones on the off diagonal. Beside and here is all 0. Then it will look like this. Okay. Yeah, this is what we do the power. Okay, diagonal matrices. That means it only has diagonal entries, and it's super easy to find inverse exponentials powers. Yeah, it's just 1 over the diagonal entries, diagonal to the power. It's the same for this. Yeah, it's trivial almost. Now let's look at nilpotent matrices. This is also quite important. So for that, all the eigenvalues are 0, and there's a finite e to the power of at. It means the rank of n is smaller than n, and the rank decreases with every power that we take. For example, one example of it is the Jordan block. It just shifts everything up. So it shifts z to y, y to x, and x to nothing. And this is never invertible, but I minus n, so identity minus n, is invertible, and it's this series. I actually got asked about this on one of the interview for for quantum finiteness and I didn't know it. But I mean, who knows this stuff? I mean, now I know, but it's been years that I did it. But it would be simply this formula. If we do exponentials, yeah, we can use this formula. Yeah, and e to the power of n is always invertible. It's just e to the minus n. What else? Jordan-Chevalier. So yeah, a matrix, we can always split it into a diagonalizable matrix and a nilpotent part. If A is like this, consisting with a nilpotent in the middle, or if we can split into this, then a to the power of k is 0 at some point. So if n to the power of k is 0, then a to the power of k is also 0. And if the derivative of x equals the nilpotent matrix of x, then the growth is polynomial and it's marginally stable. Yeah. And it's basically what this represents as a directed acyclic graph. What it means is, yeah, the variables move from one state to another, but they cannot go back. And actually I have like a Python animation for this as well. So let's look at that. Where is this? Nilpotent. So yeah, let's see this as the input, or at the beginning I just marked like different dots. Let me do it full screen. So yeah, we can see what happens. So if we multiply n to the power of 1, it would shift all the z values. So let's say here the yellow points were all at 2.5 or 3. How did I put them at 3? Okay, 2.5. So all of this will get shifted to y. So this is the y. So yeah, z gets to y. And all of these yellow dots are then on the 2.5. And yeah. And then x. Yeah, so you see what happens. If you do the power of nilpotent matrices, and in the end, everything goes to nothingness. Okay. There are skew-symmetric matrices when a to the power of t equals the negative a. Then properties are the diagonal is 0, the rank is even, and it has, if it has an odd dimension, then it's singular. The eigenvalues are either imaginary or 0, and it's normal. A transposed a equals a transpose. Then also e to the power of a transpose with e to the power of a is equal to identity. What does this mean? This means e to the power of a is orthogonal. And yeah, if it's the determinant of this is 1, then it's a special orthogonal. Then it preserves, yeah, length and angles. Basically, you can see this as a rotation. So exponent gives us an orthogonal matrix. So rotation. So a represents the axis of rotation, and e to the power of at is the actual rotation. A to the power of 2k, so something even is symmetric and negative semi-definite. E to the power of something odd, then it's skew-symmetric. And it's only invertible if n is even and full rank. And yeah. Pfaffian, we can get through the determinant. If we know the determinant, it's easy to calculate the Pfaffian. Oh yeah, and orthogonal decomposition, Frobenius inner product. You can see any matrix, we can make it into a symmetric part and a skew-symmetric part. So that's where we could also find it, for example. So let's look at symmetric positive definite matrices. That means x transpose ax, it's always bigger than 0 if x is not 0. And yeah, I transpose equals a, because when we look at this rule from before, this part needs to equal 0 because of this rule, so that means it has to be symmetric. And this matrix is invertible, and A inverse is also positive definite. The determinant is always larger than 0. The trace is the sum, it's larger than 0. All the eigenvalues are greater than 0. It's orthogonally diagonalizable. We can do Cholesky on this. A to the power of k is easy to calculate. And the same goes for the inverse exponential logs functions as seen before. And it appears a lot in optimization. So if the Hessian is positive definite, that means it's a global minimizer. And yeah, that's why it's an important matrix. There's Idempotent matrix, so if we square it or take the power of it, it equals itself. So what does this mean? So basically this is the same thing. So for every eigenvalue, it satisfies that squared equals 0 itself. So it can either be 0 or 1 only. So yeah, the characteristic polynomial exists only of lambda minus 1 to the power of the rank, and then 0, whatever is in the null space. And it's diagonalizable. The rank is the number of eigenvalues equal to 0. So the trace is also equal to the rank. The determinant is 0 unless it's the identity matrix. Yeah, and identity minus a is also idempotent. And what did I have here? So x can be split up in ax plus identity minus a. This is the image, and this is the null space. Basically, it explains it. What was this? So polynomial. Was this approximation? So function of a is the function at 0 times identity minus a, and the function at 1. Wait, this one I'm not sure. I need to look this up again. I forgot it already. Oh, this is probability of A can be written like this. So yeah, the probability of 1 times A, and the probability of not happening is I minus A. Can be written like this. Let me actually add this. So yeah, it's like the Bernoulli weighted outcome. Yeah, the power of it is trivial. E to the power of A can be written like this. Identity plus E minus 1 times A. A function of this, you see it's also the same. If we apply a function to A, it's the function at 0. I minus A. Right. Yeah, so we have a function, we evaluate it at 0 and 1, and then we multiply this, so it's also easy. Let's look at correlation, covariance, stochastics. So the variance is defined as the covariance of the variable itself. So it's x away from the mean. That's our expectation. xy is defined like this, the expectation of xy both happening minus x times y. And yeah, we can write this as in a matrix form. So we on the diagonal, we have the variances, and here we have this, covariances. The property of this is it's symmetric and it's positive semi-definite. Oh yeah, this means the mean, and this is the variance squared, and then just one is standard deviation. So yeah, and if we apply function, or if it's like from function, then A is 2, 1, for example, in here, and then we just times the covariance. So yeah, it would be the variance of this would be 8, for example. Correlation is basically also that it's normalized. That means it's between 1 and minus 1. The diagonals are always equal to 1. Can use this formula. So yeah, if this was our original covariance matrix, we just write out the diagonals for 9. We do the inverse and the root, the square root of it. We put it together, and this would be our correlation matrix. And yeah, where do we see it? Gaussian distributions. We have our mean and correlation matrix. Covariance, density function would look like this. Yeah, and conditioning, sure. We also saw this, we already went through this before. And this is everything that I had for my linear algebra recap, which is already super long. I think it's going to be like 2 hours, But hopefully you guys learned some linear algebra, got some intuition of what actually happens, hopefully understood the topic a bit more. And yeah, thank you for listening. And it also helped me if you guys have anything that I should know about on linear algebra, please leave it in the comments. Anything important. And yeah, thank you very much.